And we come to the next presentation from Osaka University by Professor Takahashi in a combined work with Kobe and Kyoto. And we are looking forward to your work on fatigue and magnesium.
Thank you, Mr. Chairman. My name is Yoshimasa Takahashi from Kansai University. And today I would like to present my study with this title, Emergence of Distinct Fatigue Limit, the Impact of Excess Solute Magnesium in 6061 alloy. And actually this presentation is the collaboration of Dr. Shikama at Kobe Steel, and also Professor Noguchi at Kyushu University, and I'm representing today. And as a background, let me first review the SN behavior of materials. The SN curve of steel, here I show the carbon steel, typical one, has the distinct knee point or fatigue limit. And this value, the emergence of distinct fatigue limit of steel is very important because we can apply the concept of a cycle-independent strength design because it has a distinct value here. So it is the one of the characteristics why so many steels are used in industry. But when you look at the non-ferrous metals, such as aluminum alloys or copper alloys, the SN behavior of such alloys, like this, does not show distinct fatigue limit, even in the gigacycle. Even in the gigacycle regime. So we have no idea. We obliged to use the finite strengths at certain cycles, for example, 10 to the 7th power cycles for design. So this is kind of the demerit of non-ferrous metals compared to carbon steels and other steel materials. But if you do a trick to our conventional aluminum alloy, you can make it possess a steel-like fatigue property, distinct fatigue limit. This is a very important point of my presentation. This modification, if possible, is very useful, as I said, because we can apply the concept of cycle-independent design, strength design. So how can we make an aluminum alloy possess such a steel-like fatigue property? Okay. So let me explain our strategy towards such a goal. From a microscopic viewpoint, fatigue limit has been found to be the threshold against either of two phenomena. That is, initiation of a small crack or the arrest of a small crack. In the case of conventional steels, it has been found that the fatigue limit corresponds to the threshold of a small fatigue crack growth. Okay? And then why is a crack in a steel easily arrested? There are several mechanisms. For example, work hardening or strain aging near the crack tip, or slip blocking by grain boundaries, or a crack closure phenomenon. What we focused here is strain aging. Strain aging, the theory of strain aging has been known from 1960s or even before, probably the oldest one. But this is a very important point. In the theory of strain aging, for example, in steels, or the solute atoms such as carbon or nitrogen, diffuse toward the crack tip and block the slip of dislocations. So when you apply or if you can apply this concept to an aluminum alloy, then maybe we can make a distinct fatigue limit. And this is very important engineering. This can be applied to a very vast amount of aluminum industry. So it is very, very interesting topic for us. And what we did first was to develop a new aluminum alloy having a strain aging property. And first, we employed 6061 as the base alloy because this material has a great property. For example, for automobile industries or other, for example, hydrogen. This is known for hydrogen-resistant material, so it can be used for hydrogen gas environment or any other harsh environments. And this alloy originally contains backbone precipitates, which is composed of magnesium and silicon at this ratio. And the concept of our new alloy is this. It contains not only the backbone precipitates, but also the extra solute magnesium, which will induce strong strain aging property. So how can we have to, in order to realize such an alloy concept, we had to design or modify the thermal process first. For the new alloy, it contains a lot of magnesium silicide in it. So if you add another amount of magnesium, the solubility of the backbone precipitates, I mean the magnesium silicide, is very much lowered. So we had to introduce another high temperature solutionizing here. And this process enables us to obtain a very high density of magnesium silicide, and also it contains extra amount of magnesium, strain aging inducer. With this process, we made another new alloy. So from now I call this a new alloy. Okay, so let's see the results. These curves show the stress-strain behavior of base alloy and the new alloys. The base alloy does not show any strain rate effect. Here, the tensile tests were done under 3 orders of different strain rates, and no strain rate effect is observed. But for new alloys, they are containing plus 0.5 and plus 0.8 magnesium. They show higher strengths. For example, the flow stress becomes higher at lower strain rate. This is completely the opposite behavior compared to the normal alloy. Slower is stronger is very important. And also we can see vibrations or so-called serrations on the curves. And the work hardening rate is also high for the new alloy compared to the base alloy. And they clearly show the strain rate dependency. So what we can say here is that the new alloy clearly shows the time-dependent dislocation solute interaction. In other words, the strain aging property. So then we conducted fatigue tests by using these special alloys, new alloys. We fabricated this fatigue specimen and introduced a small blind hole at here for a crack starter. And we used cantilever type rotary bending machine, and used this test condition to see the fatigue behavior. Okay, this data shows the fatigue behavior in ambient air at room temperature. The SN behavior of base alloy, again, shows smooth behavior. So it is one of the typical non-ferrous alloy. On the other hand, the new alloys show distinct fatigue limit here, you know? And when these curves are compared together, the new alloy shows excellent fatigue behavior compared to the base alloy. And let's see the small crack behavior. These pictures show the small crack behavior emanating from the rim of the hole. When the stress level here, 90 megapascal, is just below its fatigue limit, 95 or 92.5, the cracks initiated from the hole gradually they are retarded and almost be arrested at the run-out cycles, 10 to the 8th cycles. So we can say that the fatigue limit observed in the new alloy is a threshold against small crack growth. And also, we conducted a stress step-up test. If you do a stress step-up test by using conventional steel, the pre-fatigued specimens shows much higher strength, which is called a coaxing effect. And what we can see here is that the new alloy clearly shows coaxing effect because the pre-fatigued specimens is much stronger than the virgin ones. And this characteristic is peculiar to the new alloy, which we can't see in the base alloy. So far, I've checked the new alloy property only in the ambient air, but here I show you the results checked in dried air and nitrogen. The new alloy clearly shows distinct fatigue limit, even in the dried air or nitrogen, irrespective of the environment. And they are also found to be the limits of small crack growth. And the crack mode is mode 1 typing in the ambient air, but shear mode in dried air and nitrogen. And finally, the sigma step-up test. The new alloy shows coaxing effect, but base alloy don't. And what's interesting here is that in the ambient air, the coaxing effect is very pronounced, about 18 megapascal increase of strength. But dried air or in nitrogen, the effect is a little bit smaller. At this moment, we don't know why such an environmental difference arises. Maybe the contribution of added extra magnesium to the strengthening may be different, but yeah, it's open for discussion later. And these results, except for the final environmental effects, are contained in these papers. Thank you very much for your kind attention.
Thank you very much for the presentation. Other questions? Yes, please.
Is there any chance to test your materials up to 10 to the power of 10, for example, cycles using ultrasonic fatigue? Do you have such a possibility?
Yeah, we actually do have a ultrasonic apparatus, and we are planning to do the experiment.
It would be really interesting to see the results.
So the fatigue limit is certainly connected to these magnesium atoms, and the obstacle of these magnesium atoms to dislocations, right?
Right, yeah, that's my thought, yeah, I think so.
And you think that could be also the reason for this environmental effect, which you questioned at the end?
Yeah, it's difficult to answer, but in the ambient air, somehow the magnesium effect is strong. But in the dry air, or in nitrogen, which means that without those and the environment doesn't contain water, they show somehow smaller effect of a weaker effect of magnesium. So this is, I think, this is a very important point, and we can analyze this point further in the near future.
I didn't see further question for the moment, so thank you again very much.